Briefly, what we're looking at, we are very fortunate to have a program at the Advanced Photon Source. We have 36 shifts. We've used 9 of them so far. And the Advanced Photon Source enables you to collect an X-ray scattering pattern in 2 seconds. You do the same experiment on a rotating anode, it takes an hour. So this basically allows us to do dynamics. We now have this is now a 3rd generation oven where basically we can put in one of these proton exchange membrane materials and we can heat it in situ and humidify it in situ. And so we can either study film forming or humidification and drying processes. Now, this is important for 2 reasons. One is that the memory of the material affects its proton conductivity. So you need to know something about the morphological changes during film forming. And the other one is, even though we know that the PEM falls apart due to hydroxide, it still falls apart because you're going up and down around the glass transition temperature when you run these devices, and the things just form pinholes. So if you can actually model, if you can get an idea of the dynamics of a nanometer scale morphological changes, you should be able to extrapolate out to a micron scale model and be able to predict when pinholes are going to form. So this is basically the beamline from a synchrotron, which would be back here in the wall with electrons whizzing around at 99.9999% the speed of light. They go from an undulator, they give up energy, and beautiful X-rays come out here. And we show them from here, and we basically scatter them, and we have a photographic plate or a CCD detector. We get a pattern like this, which we transform into a Sachs pattern like this. And then we basically say cool things about this, or we actually go one step further and come out with a model of the system. And so this is something that was developed by my student Nick Aida. It's basically a clipped random wave morphological representation of a Sachs image. This is not a unique solution. It is basically a very, very possible solution. And the reason we got bold and published this is simply because it matches almost the same morphology that is predicted by the dissipated particle dynamic model, which was first implemented by Toyota and more recently by Stephen Patterson. And so this is a purely theoretical model, and this is from experimental data plus one other parameter, so it's a partial theoretical model, and the 2 models basically match, except the DPD has slightly smaller domains, but the morphology is the same. And so we believe this is a pretty powerful way of treating Sachs data to get an idea of what the structure of these films looks like. And if you extrapolate this out to the ideas of Greg Voff and Michael Akerling, you realize that what you want is to make these domains as small as possible. And so if you could actually use the Sachs to figure out what these are experimentally, then you can design your film to make smaller and smaller ones.